Good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Dr. Benoit Coasne. He obtained his PhD in physics on capillary condensation in nanoporous materials at Paris University. Then he worked as a postdoc on freezing of nanoconfinement systems at North Carolina State University. Currently, he is a CNRS Research Director at the Interdisciplinary Physics Laboratory at the University of Grenoble, France. He is the co-founder and past president of the French Adsorption Society, and he is on the board of the directors from the International Adsorption Society. His research focused on adsorption, phase transition, and transport multiscale porous material. He is co-author of 184 articles that have been cited almost 7,000 times. So once again, welcome, Dr. Coasne. Thank you so much for being here, and please feel free to share screen and start your presentation.
Yes, okay, let me share. Can you see my screen?
Yeah.
Yeah, okay.
Nicely.
Okay, so good afternoon, everyone. And first of all, let me thank the organizers for inviting me to give this seminar. It's really a pleasure, and I think it's a great initiative. Actually, one of the best initiatives I've seen in the last year. So today I'm going to speak of adsorption and transport in nanoporous materials. And let me give you a very naive and brief introduction to this. But what I call a nanoporous material is a material that consists of some solid domains, so here in gray, which coexist with some pore voids in black. And when we refer to nanoporous materials, that means that at least one of the pore dimension is at the nanometer scale. So when you work with nanoporous materials, there are essentially two very important properties to keep in mind. The first one is the large specific surface area. So typically, if you take ashes and if you could unfold all the porosity, you would get a few square meters per gram. But when you consider nanoporous material like zeolite, which are nanoporous crystalline solids, or activated carbons, which are these amorphous materials, you can reach much larger specific surface areas, typically a few thousand square meters per gram. So that's the first important property, because you understand that if you confine a liquid inside these materials, you see that most of the liquid atoms, they actually see the surface, they interact with the surface much more than with other fluid molecules. So that's the first important part, because of course, with this large surface area, there's a lot of solid fluid interaction at play. Now, the second important property is the nanoporosity itself. I mean, this typical scale in the nanometer scale is of very strong interest for physicists, because it's a very specific scale, because it's actually of the same order of magnitude as the range of intermolecular forces in liquids. So again, if you confine the liquid inside this nanoporosity, what you're doing is introducing a sort of cutoff in the molecular interactions. So because of these two effects, the surface interaction and the nano confinement, there's a lot of new adsorption and transport phenomena, such as surface-driven or confinement-driven phase transitions that occur. And I'm not going to spoil my presentations, because I'm going to show you a lot of nice examples of these effects, but let me just tell you a few words about the origin of these new phenomena. Basically, it comes from the fact that at this scale, when you confine a liquid at the nanoscale, there's a strong interplay, a strong coupling between adsorption and transport. And because of this coupling, I mean, usually when we do hydrodynamics, we basically ignore the details of all the surface thermodynamics. But at the nanoscale, you cannot ignore this surface thermodynamics. So because of this, you have a rich and complex behavior in nano-confined fluids. And as you will see, in terms of transport, when you confine a liquid at this molecular scale, you can have a lot of new effects, such as, for instance, the viscous hydrodynamics breakdown, and I'm going to discuss this later today. So the goal of my presentation today is to show you the work we've been doing in the recent years using theory and molecular modeling of adsorption and transport in nanoporous materials. And I'm going to split my presentation in two parts. First, I will discuss the thermodynamics part, and I will discuss an important point, which is usually not really discussed, which is the fluid criticality in the shift of fluid criticality in nanoporous materials. And then I will move to the second part where we'll specifically discuss the impact of confinement on transport in sub-nanoporous materials. So we're going to look really at extremely confining systems. So let me start with the first part. So usually what I do is, mostly molecular simulations. So we start with a model, a simple model of nanoporous silica. So we usually start with a block of crystalline silica. So that's cristobalite, which is a cubic phase like a quartz. And then we're going to do like experimentalists, we're going to melt the system using molecular dynamics at high temperature. And then once the system is molten, so liquid phase, we quench the system, okay, to get a disordered amorphous phase. So it's a sort of frozen liquid, if you like. And once we have this frozen liquid, this amorphous silica, we actually carve out of this material, you see a cylindrical cavity. And because I'm a physical chemist, I try to make the surface as realistic as possible. So here, typically what we do is when you carve out the system, you have a lot of oxygen dangling bonds at the surface. So here we actually saturate the dangling bonds with some hydrogen atoms so that we have a fully hydroxylated surface, more or less like in a real experimental material. And once we have this model, well, we do to look at the surface thermodynamics, we use a ground canonical Monte Carlo simulation. So ground canonical means the open ensemble. So in this ensemble, you know that the system has a constant volume. So that's going to be the cylindrical pore with the adsorbed phase, which has a constant volume. And this system is in equilibrium with an infinite reservoir of molecules that imposes both the temperature and the chemical potential. So it's exactly like in real adsorption experiments where you have the porous material and it is set in contact with a reservoir of molecules that imposes both the chemical potential, the temperature, so that the pressure is also fixed. Because if you fix the chemical potential and temperature for a fluid phase, the chemical potential, the pressure is also fixed. And then we do normal Monte Carlo simulation, except that the Boltzmann acceptance probability, of course, is defined in the ground canonical ensemble, so that in addition to the classical Boltzmann factor in the canonical ensemble, you also have, of course, the chemical potential contribution. Okay, so once we do this simulation, what we get is typically like in experiments. So you measure the number of molecules in the system, which is the fluctuating variable conjugated of the chemical potential as a function of pressure. Because as I said, we fix the chemical potential, but since the temperature is also constant, we can convert the chemical potential into a pressure. And P naught here is the bulk saturating vapor pressure. So it's the pressure at which in the bulk conditions, all the gas transforms into the liquid. So as you can see, it starts at low pressure with the rapid formation, the sharp increase in the adsorbed amount at small pressure. So here what you do is you basically adsorb the first monolayer, okay? And then once you have adsorbed a monolayer, you see that the adsorbed amount keeps increasing with pressure, but at a smaller rate, which is due to the fact that beyond the first monolayer, you adsorb at increasing distances from the substrate, from the solid surface, so that the interactions, the intermolecular interactions get weaker and weaker. That's why the slope here is smaller. And then, in agreement with experiments, we see that at pressure much lower than the bulk saturating vapor pressure, you see that you have a sharp increase in the adsorbed amount, which corresponds to capillary condensation. So capillary condensation occurs as the adsorbed film becomes mechanically unstable, so that you have the cylindrical film, and then at a given pressure, it becomes unstable, so you have pore filling at this pressure. And starting from the pore being filled with the liquid, you see that evaporation, again, that's in agreement with experiments, you see that capillary evaporation occurs at a much lower pressure so that you have this large hysteresis loop. So usually when you look at the classical thermodynamic literature on these problems, usually the adsorbed film formation is described using the BET model, which is a statistical mechanics model. It's actually, you can show that it's strictly equivalent as the Ising model. And the part dealing with condensation is usually described using a classical argument based on the Laplace pressure. So the Laplace pressure describes the pressure difference across this curved gas-liquid interface. So you have this difference, which is related to the gas-liquid surface tension, and D here is the pore diameter. So this is the Laplace condition, but if you add to this condition the chemical potential equality, because of course here you have phase equilibrium, so the molecules in the liquid phase and in the gas phase, they are free to exchange, okay? So at equilibrium, you have chemical potential equality. If you combine these two equations, assuming that the gas is an ideal gas, you end up with the very conventional Kelvin equation, which relates the log of the capillary pressure to this capillarity term, where again, I repeat, you have the gas liquid surface tension, rho is the liquid density, and D is the pore diameter. So as you see it here, you need two models, two thermodynamic models to describe this, these two parts of the curve. But actually, a long time ago, it was recognized by Diagon, who was a Russian physicist, that there's one failure in the Kelvin equation, which is that the Kelvin equation does not describe the formation of an adsorbed film. That's why you need actually two models. So it was recognized by Diagon that there was something missing in Kelvin equation. So what he did was the following. So he developed a model where you write the ground potential, because you remember I said that you have to consider the system in a ground canonical ensemble. So the potential, the thermodynamic potential that has to be minimized at equilibrium is not the free energy, it's the ground potential. So it's the free energy minus the chemical potential times the number of molecules. And when you do the thermodynamics, so we know that in this ground potential, you have the pressure time volume contribution for the gas and for the liquid phase, which is the adsorbed film, plus you have two surface contributions, which corresponds to the surface contribution from the gas liquid interface and from the liquid surface, liquid solid surface, sorry. That's why you have two terms. So if you stop here, if you get rid of this term, believe me, it's the same as Kelvin equation, okay? But what Diagon did was to add a fifth contribution, which is also a surface contribution, which accounts for the fact that when the film thickness here is very small, the two interfaces, the solid liquid and gas liquid interfaces, they see each other, okay? So it means that there's a coupling between these two interfaces. And a long story short, this surface coupling is actually related. You see the derivative of the surface potential is directly related to what is known as the disjoining pressure. So we call it the disjoining pressure because depending on the sign of the surface potential, you see that this term will make the two surfaces separate from each other. In that case, it's called disjoining. But we now know that in some cases, you have a system where it's actually joining, so that this force will tend to make the film disappear, okay? And in that case, you would call it a joining pressure, okay? So usually we use for the surface potential something that is related to the van der Waals interaction, but it was actually proposed a long time ago by Pierre-Gilles Deugène that you can use a very general form with this exponential decay. So T here is the film thickness, and basically you see that here, of course, you recover that as the film thickness becomes infinitely large, of course, the coupling has to disappear, okay? So it has the correct mathematical behavior, if you like. So the prime is that this parameter here, which is related to the spreading parameter, which is exactly the spreading parameter, we actually don't know this value. It's a specific constant that depends on the fluid and on the solid and on the temperature as well. So what we did here was to use one of our simulated adsorption isotherms. So this one is for a large pore, okay? And we basically fitted the model, which is the red line. And as you can see, we get a very nice agreement, okay? I mean, the model works pretty well. So thanks to this, we now have a value for the spreading parameter. And what we did next is, of course, now there's no fitting anymore because we know every parameter. And we checked here that our model, I mean, this Diagon model, which is the red line, does describe the capillary pressure as a function of pore size. So the blue circles are the molecular simulations data. The red line is the model. So we see that we have a nice agreement. And if you add onto this plot the black crosses, which are some experimental data for MCM41, is a ordered silica material with very simple cylindrical pores, you see that we get very nice consistent picture between theory, molecular simulation, and experiment. So now let me show you what we get when you consider at constant temperature different pore sizes. Okay, so you see here you decrease the pore size from 10 nanometer down to 1.6 nanometer. So as you can see, for the large pore, you have this large hysteresis loop, which I already described. And here, clearly, the picture is the following. So as I said before, upon adsorption, you have this. So sorry, it's a slice, okay? That's why it looks like it's a slit pore, but it's actually a cylindrical pore. So you see that you have this adsorbed film. And as I said, capillary condensation occurs as the film becomes unstable. And starting from the filled pore, you see that evaporation will occur by the displacement of this curved interface, so a hemispherical meniscus, through the pore axis, okay? Now, if you keep decreasing the pore size, you see that the hysteresis loop actually becomes very narrow, and then at some point, it even disappears, you see? There seems to be a critical diameter, DC, which is somewhere here between 2.4 and 3.2 nanometer, so let's say around 3 nanometer, and below which you see that adsorption is no longer a first order phase transition because you don't have this hysteresis loop, but it becomes reversible and continuous. So exactly like a second order phase transition. So that's interesting. That's the same data because it means that if you turn your head to the left, you can draw this red curve, which looks like an envelope with a phase diagram. So for large pore diameter, you can define two densities, a low density and a high density, okay? And then there's a first order transition between these two densities. But for pore size smaller than this critical diameter, you see that, again, as I said in the previous slide, you seem to observe a second order phase transition. So this is data for different pore sizes at constant temperature. But of course, you can do the same for the same pore size, but at different temperature. And then what you get is the following modified phase diagram. So again, this is the phase diagram. So you have the temperature and the density. In black, it's the bulk phase diagram. So you have a critical point here, okay? And basically upon confinement, you see that there is a shift of this critical point towards a point that we call capillary critical point, okay? Which is shifted towards lower temperature. So that's something that was predicted a long time ago by Bob Evans using statistical mechanics. And what Bob Evans predicted is that the shift in the critical point normalized to the bulk critical point is proportional to 1 over the pore size, okay? So we wanted to verify this. So what we plot here is this shift in the critical point normalized to the bulk critical temperature as a function of 1 over the pore radius, okay? So it's not the pore diameter, but of course it's proportional. And because we're going to compare data for many different fluids and many different nanoporous materials, what we did is to use something normalized here. So you see, it's the pore diameter or pore radius is normalized to sigma, which is the size, the kinetic diameter of the confined molecule. And when you do this, so in white, it's experiments, okay? Taken from the literature, again, for many different fluids, many different porous materials. And you see that we do seem to verify the prediction by Bob Evans, as there is a simple linearity between the critical shift and the reciprocal of the pore size. And in red, it's molecular simulation, and there's a shift in it's not exactly the same slope, we think is due to the fact that you don't have the same statistical fluctuations in the experiment and in the finite size simulations. But you see that we also confirm that there is a simple linearity between the critical shift and the reciprocal of the pore diameter. So what is interesting is even if you have this shift in criticality, you can still, I'm going to show you in this slide and the next one, that you can still use capillary argument. So here what we did is to do both experiment and simulation for many different fluids, going from very simple fluid, nitrogen, to more complex fluid like aromatics, like xylene. And you see that we also have in the loop, we also have acetone and a hydrocarbon chain. And we considered many different zeolite materials, so very narrow pores. As you can see, the pore size is at most 1 nanometer. And we looked at different materials, so different structures. And here what we plotted is, so that's the Kelvin contribution. You remember, it's the log of the capillary pressure. So it's a chemical potential here. It's the chemical potential at pore filling as a function of this capillarity term that appears in the Kelvin equation. Okay, so it's the surface tension divided by the pore size and normalized to the liquid density. And the striking result here is that you see there seems, even if you're looking at extremely tiny pores, there seems to be a simple Kelvin relation between the chemical potential at pore filling and this capillary contribution. Again, I need to repeat that this is a very strong result because that's completely unexpected. So to better understand this result, we went back to this Diagon model, which is a macroscopic model by construction that I introduced before. So you remember you have this ground potential that needs to be minimized. And if you solve this model, you can predict the capillary pressure here, okay? I mean, it's actually the chemical potential at the capillary pressure. And you see that you have two contributions. So the first one here, it's simple. It's Kelvin equation, okay? So it's pure capillarity. But then you have a second contribution, which is the surface contribution. And this second contribution, inside the second contribution, you have the film thickness at the capillary pressure. And you have psi, which is the range of intermolecular forces between the solid and the adsorbed phase. And D is the pore size. So what do we learn from this? What we did was to plot using this model and using some molecular simulation. We plotted here the film thickness at the capillary pressure normalized to the pore diameter as a function of pore diameter. Okay, so for very large pores, the capillary pressure is at large values, but because for large pores the pore diameter is so large, you see that the film thickness divided by the pore diameter becomes smaller and smaller. Okay, so it's basically where you get macroscopic porosity with extremely large pores. Now for intermediate pores, like nanometer pores, what you get is you see that here there's actually an optimum. So it means that when you look at capillary condensation in a pore of, let's say, 2 to 4 nanometers, you can no longer neglect the thickness of the film adsorbed with respect to the pore size. Okay, but what is striking is if you keep decreasing the pore size, like for zeolites that I showed in the previous slide, you see that capillary pressure is shifted to such low pressures that the corresponding film thickness is vanishingly small. So what it means is that in extreme confinement, the pore filling occurs at such low pressures, but the film thickness is negligible, okay? And this is exactly what you see here. And again, the diamonds here are some simulation data. So basically, if you go back to this equation, what does it mean? It means that for large pores, you can neglect the film thickness and the range of intermolecular forces with respect to the pore diameter, and you recover Kelvin equation, okay? But for extremely small pores, of course, you can no longer neglect the range of intermolecular forces, but because of what I just said, you can still neglect the film thickness with respect to the pore diameter. And in that case, if you do a Taylor expansion, you will show that the capillary pressure includes two contributions. One, which is directly the Kelvin contribution, so the capillarity effect, pretty much like for large pores, plus a constant K, which obviously this constant K does depend on the surface interaction. But let's say that as a first order explanation, you see that even if this constant K depends on the fluid and on the solid, and by the way, this is responsible for the scattering of the data with respect to the capillarity line here, but you see that overall, as a first order approximation, you are always driven by the capillarity contribution. So in short, the take-home message is that even if you have extremely small pores where surface adsorption is a key contribution, there's always a leading contribution, which is capillarity. So now let me move to the second part of my talk, where I'm going to discuss transport in sub-nanoporous materials. So again, we're going to look at extremely strong confinement. So usually the way you describe transport in nanoporous media is using Darcy equation, okay? So Darcy equation, in short, is a Onsager-like transport equation. So basically, it assumes that you have a linear response between the flow rate, which is what you observe, so it's basically the permeability, and the pressure gradient. So there's a pressure gradient that induces transport, and what you observe as a result is the flow rate, okay? And again, Darcy law simply assume that there's a linear response between these two quantities. And in this equation, usually when you use it as an engineer, you assume that you can split the two parameters here into two important parts. So K is the permeability. So if you look at the units, it's basically in square meter. So it's the, if you connect this, for instance, to Poiseuille flow, it's directly the section area that conducts the flow, okay? So usually K is assumed to be a constant that only depends on the fluid, on the material, so on the porous solid, not on the fluid. And on the other hand, eta is the fluid viscosity, which is assumed to be the bulk fluid viscosity. So as an engineer, usually you basically split these two contributions by saying, okay, there's one that depends on the solid, one that depends on the fluid. However, if you do this kind of molecular measurements on a strongly confining material, like this realistic molecular model of kerogen, which is basically a carbon material that is a sponge-like materials, what you get is the following. So we looked at so that's the flow rate here, V, normalized to the pressure gradient as a function of 1 over the viscosity, okay? And we consider different fluids. So here you have methane, propane, hexane, nonane, and dodecane. So alkanes with an increasing chain length, okay? So in black, it's Darcy equation, okay? So here we use simply K, we use the, as I said, it's the section area that conducts the fluid, okay? So it's basically, it's related to the pore size to the power 2. And there's a numerical factor that depends on the shape of the porosity, which is obviously ill-defined here. But what is striking here is you see that in contrast to what is usually assumed, that K is a constant that only depends on the material, on the porous material, you see that here we cannot reconcile the data. So when you look at different fluids, you get different permeabilities, okay? So it's in stark contrast with what I said on Darcy being used from an engineering point of view. And even for the same fluid, you see, methane or propane, for instance, when you change the density, even if you use the correct viscosity here, you see that the permeability does depend on the fluid density and the fluid viscosity. So it means that when you look at Darcy equation, and this, again, Darcy equation is a strong relation, okay, because it's really a Onsager coefficient, okay? You see that all the concepts that we use, like permeability, viscosity, they become strongly coupled, okay? So in the next slide, I'm going to try to explain to you the origins of this strong coupling. So usually, one thing you can do is to derive Darcy equation is to start with a NavierStokes equation, okay? So it's a momentum conservation equation. So here you have the change in the momentum as a function of time, and it's related to the forces that apply to the fluid particles. So you have the pressure gradient, which is what imposes the transport. Then you have the viscosity term, which basically describes the relaxation inside the fluid particle. And then you have this friction term, which describes the friction of the fluid that is moving inside the nanoporous material. Okay, so this one is more like a fluid friction term, and this one is a fluid solid friction term, if you like. If you solve this equation in a direction perpendicular to the pressure gradient, so you can get rid of this, and that you solve this equation in the Fourier space, you get a very simple prediction on the Fourier component of the flow rate. They should verify the following equation. Okay, so it's the Fourier component K of the flow rate, which I call JK, at time t equals 0 and at time t later. And from this equation, you get that this Fourier component of the flow rate should decay in time exponentially with this contribution. Okay, and this is very strong, what I'm saying here, because it's really at the roots of Darcy equation. You have this assumption of viscous flow approximation. So that's a strong prediction. But if you look at what you measure in molecular simulation for this time autocorrelation for the flow rate, you see that you get something that is not exponentially. Of course, it decays with time as expected for a time autocorrelation function, but you see that the time dependence has nothing to do with the simple exponential decay, okay? And I want to insist here that I want to convince you about this, that this is what is at the origin of the breakdown of this separation between permeability and viscosity when using Darcy equation for extremely small pores. So to go one step into this, in fact, the reason of this viscous breakdown, as we call it, or hydrodynamics breakdown, is the following. When you use NavierStokes equation, which I recall is simply a momentum conservation equation, what you do is you actually assume that there's a time scale separation between the time it takes to transfer momentum between particles, okay? So that's the momentum transfer term here in blue, and the time scale it takes to relax the fluid, I mean the stress inside the fluid particles. So when you use NavierStokes equation, it's probably not obvious, but what you do is actually you assume that this time, the time it takes to do this is extremely fast compared to the time it takes to transfer momentum between particles, okay? So for the relaxation time, it's clear, it's related to the viscosity. As we know, in the Green-Kubo formalism, the viscosity is directly related to the time correlation function of the stress applied to the fluid particle, okay? So it's, as I said, it's really related to the time it takes to relax the stresses inside the fluid particle. Of course, the value you get for the typical relaxation time depends on the fluid, density, temperature, etc. But on average, I mean, for most fluids at room temperature, the typical time is it's a molecular function. So it's typically of the order of picoseconds. On the other hand, the time for the momentum transfer, which again is related to what I showed you in the previous slide, you have this time correlation functions for the Fourier component of the flow rate. And you remember we had this exponential decay. So here you see that you have a characteristic time. I mean, here it's inversely proportional to a time. So you can define a characteristic time, which depends on the fluid density, the viscosity. So again, when you do hydrodynamics, which is a macroscopic theory, what you do is to assume that this characteristic time is much, much, much larger than the relaxation time. And of course, when you do hydrodynamics, it means that you're looking at wave vector, the K vector, that goes to 0, because it's a macroscopic theory, right? So here, when K goes to 0, you see that indeed the momentum transfer time becomes infinitely long, okay? So for large pores in hydrodynamics, you do have this time scale separation. But now let's consider a nanoporous material, okay? So it means that K for nanoporous material, K, the wave vector over which momentum transfer occurs, is roughly inversely proportional to the pore size, okay? So it means that K here, instead of being very small, it's actually very large. So it means that when you look at transfer inside a nanopore, you can no longer assume that this time is infinitely large compared to this one. And that's why at the nanometer scale, you have the strong coupling between relaxation and adsorption and fluid transport. So in simpler words, what I'm trying to say is that when you look at a fluid inside a nano cavity, what happens is that because you're looking at transfer and displacement over very short distances, typically 1 nanometer, on this short time scale, you can no longer assume that you have full relaxation of the stress applied to the fluid particle. And that's why you have the strong coupling between relaxation and transport. And so what can we do? Because that's bad news, right? Because this Darcy equation is very convenient, but here I just convinced you that, I hope that I convinced you that you can no longer split the prefactor here between the flux and the pressure gradient into two contributions, one that is a fluid property and one that is a solid property. So it means that you can no longer use hydrodynamics framework. But the good thing is when hydrodynamics fails, you can still use statistical mechanics. So what I'm going to do here is to rewrite this Darcy equation by replacing these two parameters, so the permeability and the viscosity, by a single parameter, which I call big K, and which is the so-called permeance. So small k is the permeability, and big K is the permeance, okay? And the good thing with big K is I no longer need to split into a permeability and a viscosity. I can use it as a single concept, which is actually what you measure experimentally. And I'm not going into the detail, but that's one of the strong results from the fluctuation dissipation theorem in statistical mechanics, that there is an exact relation between the permeance and the so-called collective diffusivity, okay? And here rho is the density. So basically, again, I don't want to go too much into the detail, but what you do is you write that if you have an incompressible fluid, you can relate the pressure gradient and the chemical potential gradient through the density, and this is what allows you to write this equivalence between the permeance and the collective diffusivity. So the collective diffusivity, what is it? We know exactly from the Green-Kubo formalism that it's directly related to the time autocorrelation of the velocity center of mass, okay? So you take the velocity, the center of mass of your fluid at a time t equals 0 and a time t later. Of course, it's a decaying function with time, but if you measure this, you get directly the collective diffusivity. Now, this is a complicated function because in the collective diffusivity, you have the self-diffusivity, ds, which are like all the, it's the correlation in the velocity of a molecule at a time t equals 0 and the same molecule at a time t later, plus you have all the cross terms that involves correlation between molecule I and molecule J. And this was good news for us, that in the case of extremely confining material, as you can see, the collective diffusivity and the self-diffusivity, they're actually not so far. And the reason is that when you have an extremely small cavity, usually you have 1, 2, or 3 at most molecules. So most of these molecules, and that's related to my introduction, that most of these molecules, they interact strongly with the surface and not so much with the other fluid molecules. And as a result of this, again, that's a first order approximation, but as a result of this, you can actually neglect the cross terms in the collective diffusivity. That's why in the end, you can assume that the collective diffusivity and the self-diffusivity are not strictly equivalent, but close to each other. So now the good news is it's actually, we can try to build, it's difficult to build a model for the collective diffusivity, but for the self-diffusivity, we do have some models that work quite well. So if we have a model for the self-diffusivity, we can assume that the collective diffusivity is the same. And then, because of this relation, we directly have a model for the permeance. And that's what we did. So a long story short, we actually tried different models. But we found that a simple free volume theory works quite well. So again, I'm not going into the detail, but it's a quite old theory from the 60s, I think, if I remember correctly, where basically what you write is that the self-diffusivity of the molecules here is related to the self-diffusivity of a system at zero loading. So it's an isolated molecule, if you like. And you have this exponential term. So V mol is the volume occupied by the N molecules. And V3 is the reciprocal. So it's the porous volume that is available for this N diffusing molecule. And so, as you can see, if you increase the density, of course, the volume occupied by the liquid increases, and the volume available, the free volume available, decreases. So that when you increase the number of molecules in the system, you do predict that the self-diffusivity goes down. Okay. So what is interesting is that this free volume, when there is no molecule or when you have N molecule, they're actually directly related to the adsorbed amount. So if you are able to measure the adsorbed amount in the material, you can actually predict the change in the free volume. So again, here that's simply the porous volume of your material when it's empty, okay, which is usually known. And with this, if you know the adsorbed amount, you can directly predict the change in the molar volume occupied by the volume occupied by the liquid and the porous volume available to the liquid. And so what we did here was to actually measure this free volume as a function of the molecule inside, the type of molecule and the number of molecules. And we plotted the permeance here. So all the symbols, they are the data that I showed before, okay? So it's from a non-equilibrium molecular dynamics measurement where you measure directly the flow rate. And so the symbols, you see, the different colors are for the different fluids that I showed before. And for each color, you have different points because you remember we consider different densities, okay? And the line here is actually the prediction from the model, okay? Where we predict the self-diffusivity, and assuming that the self and collective diffusivities are equal, we can predict the permeance. So here we have a simple statistical mechanics model, which relies on very strong argument, like you know, the fluctuation dissipation theorem in statistical mechanics. And the good part with this model is that it actually does not use macroscopic concepts such as the viscosity, which is ill-defined at the molecular scale, and relies on very simple concepts such as free volume that can be assessed experimentally. And with this, I think I'm running out of time, so I will probably skip my conclusion here, and I will thank you for your attention.
Thank you so much, Dr. Coasne, for your presentation. It was very interesting, and we are now open for questions. So if you want to ask one, please feel free to enable your microphone or write it down in the chat. And our YouTube viewers can also ask questions, of course. So who would like to be the first one?
Yeah, can I go first?
Please go ahead.
Yeah, so Professor Coasne, and sorry that if I pronounce your name wrongly. So I'm Charlie from University of Alberta, and first of all, thank you very much for your presentation. It's a very interesting talk for sure, and I would say our group has been following your nice works in the past few years very closely, and we are actually like learning a lot of materials from your papers. So I have a few questions, and the first question is like recently we're also working on the methane diffusion within the halogens, and we're also like looking at your 2015 Nature Communication paper very closely. But actually talking about methane flow or transporting halogen, I think it's a very complicated problem because you have the advections and you also have the diffusions. And I personally strongly agree with you that it's better to use permeance as the concept. I think is it the concept of permeance is similar to the transport diffusivity? And say if we use the simulation, how can we better simulate the a gas transport within Kelvin, this kind of problems? And the second question is a little bit out of scope of your talk, but you know that you developed the Kelvin model, and we know that the Kelvin actually can change its morphology, right? So is there any good way, or are you thinking about combining this kind of morphology change with the transport, or definitely there is a study in terms of absorption, but what about the transport phenomena? Yeah. Thank you.
Thank you. I mean, two very good questions. So let me start with the first one. Okay, it's a complicated question because when I use this, okay, let me sorry, to go back. Okay, when I use this simple relation, I'm not assuming anything about the type of transport, the underlying type of transport. Okay, so here I'm just writing that if I apply a pressure gradient that is twice, provided that I stay to the linear response regime, then I should observe a flow rate that is twice. Okay, and that's probably the first thing that we should always check. Are we still in the linear regime? Now, having said this, I fully agree with you that depending on the fluid density, which is again related to temperature and chemical potential, right? I might have completely different types of transport. So what I'm trying to say is that that's what I was trying to convince you that when we use the separation between K and eta, we're actually assuming that the flow behind this, the underlying flow, is viscous. But we all know that in kerogen or in many complex systems, it doesn't have to be viscous. So when you use big K instead of this, the good thing is you're just not assuming that you have a viscous flow. You can have a gas flow. You can have gas flow with the Klinkenberg correction, which is slippage. You can have compressibility effects. I'm not saying anything about this. So now to answer really your question, the complexity, if you like, is what I'm trying to say is that once you have K, you can measure K with the collective diffusivity. And in this function, the collective diffusivity, you can have a lot of complex physics, okay? But the good thing is, for instance, that's what I'm trying to do in my research, that if we do neutron scattering, for instance, we can measure D0. So we have an independent measurement of the permeance without actually measuring the permeance, which is nice, right? Now, in your case, again, you measure K, but it doesn't mean that it's purely viscous or that it's purely Knudsen or whatever. Then it's the physics. So the physics, you will get it by looking at the shape of D0, because D0 has a very specific behavior depending on whether it's liquid flow or gas flow with slippage, etc. Because then, for instance, when you look at the temperature dependence of a Knudsen diffusion, self-diffusion, and liquid diffusion, it's absolutely not the same temperature dependence, right? So general formalism that I gave today, I think is valid almost everywhere. I mean, it fails basically when you have non-linearity effect, and when, let's say, if you have a composite material, etc., it can be much more complex for this. Now, for the second part of your question, which was, oh yes, the fact that the kerogen evolves. Yeah. So when we started to look at this, it was like 5, 6, 7 years ago. We decided to use a constant material because we wanted to look at this. But I agree with you that we're actually trying to do something now. It's not exactly on kerogen, where we're actually looking at the effect of mechanical deformation on transport. And it does affect the results. But honestly, in the case of kerogen and shale gas in general, yeah, it's a very complicated thing, because if you're telling me that the material evolves, I mean the collective diffusivity evolves as a function of time, that makes it extremely complicated. But still, using molecular simulation, you agree with me that we could have different replicas that are representative of the system, let's say, at different times, meaning different extraction times. And then we could always predict the permeance as a function of time with these different models and see if somehow we are capable of matching some real data, real engineering data.
Yeah, thank you for your answer. So, but just follow up the second question. Actually, I had some discussion with one of your collaborator. His name is Mark from University of Bordeaux. And he told me that one interesting thing is that for your model, it can match the chemical properties very well of the Kelvin, but the mechanical property may not. For example, I think if you drop your Kelvin molecules into, say, octane, it would dissolve, right? But we know that Kelvin is not like dissolvable in this like a non-polar solvent. So is there any plan that you wanna maybe considering matching the chemical as well as the mechanical property of Kelvin in future?
So this this kerogen model that we built, I mean, I think it was nice in the sense that it was really a first step, first time that someone to do this. But Jean-Marc and you are perfectly right. I mean, we're not claiming that it's the perfect model. But I would be careful by saying that it dissolves in octane, because as you know, in molecular simulation, it's going to be strongly dependent on the force field, on the reactive force field that is used by Jean-Marc. I mean, Jean-Marc is a good friend of mine, but honestly, I'm not 100% convinced that ReaxFF is capable of describing this kind of complexity. As you know, ReaxFF is a very powerful framework, but it's actually good at what it was developed for, you know. And for kerogen, I mean, we know that it's complex material. So, and maybe the materials that we built with my former postdoc Colin Bouzige, maybe there are some defects that make the system not so stable. But you see, it's not because you have some defects that make the system, let's say, not perfect, and we should probably try to cure them, that the whole matrix is wrong, you see? And to be very honest with you, for us, it was more like I mean, these models, they were nice because for us, they were like kind of real model to look at very complex systems, because as you know, because you seem very well aware of the literature, most of the literature before this was done for slit pores, right?
Yeah, yeah.
So for me, I mean, you see, I'm not saying that these materials are great. I'm just saying that it was already a nice improvement to okay, let's try to see something really disordered, you know. And now, of course, I agree with Jean-Marc that the chemistry and mechanical properties are not, of course, not completely okay. But honestly, I wouldn't say they're not completely wrong either, I would say.
Yeah, they are actually truly very pioneer works, and we have been benefiting from them a lot. So yeah, thank you very much for your answering.
More questions?
Hello.
Hello, Professor. Please go ahead.
Professor Coasne, I have two commentaries on you. In your hydrodynamic model, you use Navier-Stokes equation. What kind of boundary conditions can you use for this? Will they be consistent?
That's a very good question, because actually you cannot use a boundary condition. There's no boundary condition. The reason I involved you need the boundary condition, for instance, when you want to write the equivalence with a Poiseuille flow, right? Because in Poiseuille flow, you do have a simple geometry with boundary condition, I mean, without or with slippage, but that's it. Here, this part, I was not trying, actually, in my simulation, I don't need to use hydrodynamics, okay? I do non-equilibrium molecular dynamics. By the way, I did not mention, but we use both the equilibrium molecular dynamics with green Kubo or non-equilibrium molecular dynamics, and we got the same, okay? So the reason I used hydrodynamics here was just because I wanted to explain why in a nanopore you get this breakdown of the viscous flow approximation. I don't need, I mean, what I showed here was not to was not to try to apply a boundary condition or a specific pore geometry. I was just trying to convince you that if you follow this for a slit pore, for instance, or cylindrical pore, you do predict that regardless of the boundary condition, and I insist, regardless of the boundary condition, you must have this kind of time decay for the Fourier component of the flow rate. So basically, I mean, you know, this complicated derivation just tells you that inside the fluid, when there's, because of momentum conservation, when something happens at the surface, the momentum conservation takes time, okay, to relax through the entire material. So the reason I used this derivation was not to try to rationalize my data, my simulation data. It was to convince you that if you have a Darcy equation where you have this simple, you know, Poiseuille flow picture, then you should verify this, okay? I was not trying to use hydrodynamics. Actually, the conclusion here was more like, okay, because I know that I cannot apply the boundary conditions, I have to stick to an effective linear response model. And this, when you write this, you see here, when you write this, you don't need a boundary condition. You're just saying, I have a piece of material, it's complicated inside, I'm applying a pressure gradient, and I'm just measuring a number of molecules passing per unit of surface area and per unit of time. I don't need a boundary condition when I use, when
I have another question.
Yes.
About your free volume theory.
Mm-hmm.
My memory is from old, as a graduate student of Kirkwood's, the original Kirkwood's idea of free volume. Are you talking about empty volume, or are you talking about expansion volume, or are you talking about fluctuation volumes? Or the expansion volume and the empty volume and the voids, are they important in this material like kerosene?
Yeah, so what we, honestly, I'm not sure I can explain this question, but what we did was, I think it's among the different things you said, I think it's the empty volume. So what we do is we have the system here, which is filled with molecules. And for every number of molecules, we basically insert a probe molecule. And then if we see that it overlaps with, I mean, we do this millions of times. It's a Monte Carlo approach, okay? And if it overlaps with either the wall atoms or the fluid atoms, then we say, okay, it's not free volume. But sometimes, once in a while, we find a spot where actually you can insert a fluid molecule, okay? And that's why I say, I think this free volume is really the empty volume, accessible to the N diffusing molecules.
Okay. So you feel that free volume alone can explain in things like kerosene. You don't need energetics.
Okay.
It's energy or something like that.
It's a good question. It's a profound question, because we need to be careful. It's not because it's a free volume theory that there is no energy. Actually, the energy is in there, right? Because here what I'm doing is I'm looking at the diffusion. Sorry, I think there's a N missing here, which is the number of molecules. When I write the free volume theory, I'm just relating the diffusivity for the N confined molecule, like here, and the diffusivity of an isolated molecule. But you see that in DS0 here, you still have the adsorption energy of this isolated molecule, plus the adsorption, the energy is also in there, right? Because the way you adsorb the N molecules will depend on the chemical potential, but also on the adsorption energy. So I wouldn't say that the free volume omits the interaction energy. It's more like that it's inside the parameters. And what we're doing here is just to compare the permeance as a function of the free volume. But again, keep in mind that for all the different fluids, you have, of course, the interaction energy in there and in the adsorbed amount.
Thank you very much, Professor, for clarifying.
Mm-hmm.
Anyone else would like to ask a question?
Yes. Thank you, Benoit,
Go
for
ahead.
this nice presentation. In confined fluids, due to two kind of repulsive interactions, you may find a second critical point. Could you find this? And I don't think you may find with this Laplace or Kelvin equation.
No. Yeah, it's a good question. No, I'm not aware of this, of a second critical point. Actually, if you have literature on this, I'd like to see it, because no, I don't think, I mean, around me, I don't think people have looked at this. And for sure, I mean, you are right. You know, the reason I mentioned this, it's because I think it's good to connect to, you know, the classical thermodynamics, but you are perfectly right that even the improved model by Diagon, which is nice because it compared to Kelvin, it does, you know, for me, what I like with Diagon's model is that it actually combines in the same model the BET part and the Kelvin part. But you are perfectly right that none of these models, even the refined one, predicts the shift in the criticality. They just assume that it's a good question, because, you know, for instance, here I showed you that so you have this change between irreversible discontinuous and reversible continuous, but in fact, you know, when I showed you that the Diagon model works very nice, it works nice quantitatively, but the Diagon model completely fails to predict that it becomes discontinuous reversible, because Diagon model, like Kelvin equation, will always predict that you have a discontinuity. It's a first order phase transition. And that's why what I showed you here with this, what we called in the paper, the reminiscent capillarity, it was kind of, you know, provocative title because we were, I mean, even myself, you know, when I found out about this data, I was shocked, because I was like, no, okay, I'm not going to write that there's capillarity in there, right? Because it's not even a first order phase transition. And it was kind of contradicting my own work, right? Because I keep telling that there is a change with the critical point, blah, blah, blah. And then I say, oh, it's just capillarity. But you have to admit that even if it's becoming like a second order transition, perfectly reversible, perfectly continuous, still, there seems to, that's why we call it reminiscent. It's an intellectual word, but it's reminiscent in the sense that still, quantitatively, it follows the simple capillarity contribution. That's it.
Okay. My other difficulties with this approach is in very small length scale, very small pores. I don't know if we can define interface tension.
Yeah, I know, but in everything I showed, I always use the bulk gas liquid surface tension. You know,
okay.
At first I was like, okay, let's use, you know, Tolman equation. You know, Tolman equation is a correction to the surface tension to account for strong local curvature. But actually, the truth is you don't even need this. In every showed here, you know, like for instance here when I showed so again, circles are the simulation, so I don't need a surface tension, right? It's the result of molecular interactions, and the red line is the model, and here I use always the same surface tension. I don't have to correct it, but I agree with you. I mean, you know, I mean, don't get me wrong. I'm not trying to say that we should only do classical thermodynamics, macroscopic. I'm just saying all these old models, but it's the same with Darcy. You know, Darcy is from the 19th century, right? So it's, I think it's 1840 something, right? I'm not saying that they work perfectly. It's related to the question on the, you know, on kerogen, right? That we're not, I mean, when I was asked about, you know, having non-viscous flow, gas flow, etc. It was a good question. I'm not saying that that Darcy works beautifully. I'm saying that there is something strong in these relations. So here it's clearly that even if the surface tension is ill-defined at the nanoscale, it seems to work. And for Darcy equation, again, I'm not saying that all these parameters make sense, but I'm saying that what is left here, the simple linear relation, is strong.
Okay. About this, I wonder this breakdown with the NavierStokes equation. If we could include the interaction with the matrix, maybe you have another time scale due to this interaction. So, maybe it still works. I don't know. I'm thinking about not exactly NavierStokes, but similar, like Latz-Boltzmann equation.
Yeah, no, you're
because
right.
Latz-Boltzmann equations is easier to include interaction between the fluid and the matrix.
Yeah, it's a good comment. What is missing, in fact, what is missing is not really the friction with the matrix, which, by the way, is here. You see, that's this psi parameter, which is a friction. What is missing is the memory effect in the time autocorrelation functions here. Because in fact, you remember what I said? I said that when we use this, what we do is we assume that viscosity relaxes super fast and not the momentum transfer, right? But in fact, the simple picture that I gave where you have the displacement of a molecule over 1 nanometer and that on such a short time scale, you cannot assume that you have full relaxation of the stress inside the fluid particle. One way to account for this, and that's strongly related to what you just said, one way to account for this is to add in there memory effect. And this is known, that in system like colloids or something, if you have strong memory effect, then you have some very strong result. But let's say that, yeah, I could always reconcile this. I could use a viscosity that is corrected for these memory effects, and then normally I should be able to recover, let's say, an effective viscous flow behavior.
Thank you. Very nice talk.
Are there any more questions?
Oh, I'm sorry. Can I ask one more question? Sorry.
Please go ahead.
Yeah. So, Professor Coasne, so talking about the Capillary model, could you just clarify that if you still use some modification to the Huygens model, there is no shift in terms of capillary pressure? Sorry, the critical temperature. That's what you are saying.
Where did you? Sorry, can you repeat?
So talking about the Kelvin equation with some corrections. Yeah. So is that model still cannot predict the shift of the critical temperatures?
No, it's a good question. No, we don't use this. When we use the Kelvin equation or equivalently this Diagon model, that's one of the failure, if you like, of the approach. That, as I said, quantitatively it works, but again, with this we fail to describe the shift in the criticality. So we actually tried with my colleague a long time ago. We tried, you know, to include an effect that the surface tension goes to 0, not at TC but at TCC. We tried, because that would be a mean, right, to describe this. But okay, that's nice in theory, because then by construction, right, the surface tension disappears at the critical point TCC. So then it should work. Except that if you do this, then you are not capable of describing correctly the capillary pressure.
Okay, so actually for that, we have another similar study we published in Chemical Engineering Science.
Yes.
And we also use the Kelvin equation with the capillarity, but the other way we use the Penn-Robinson equation of state, which is the real equation of state, combined with the capillarity. We found that the PREOS with the capillarity model actually predicts there is one limiting temperature. Beyond that temperature, there is no phase transition.
Okay, interesting.
Yeah, so maybe that's we proved mathematically there is the maximum capillary pressure you can have in a pore. That's based on the van der Waals curve, and I can share that paper with you. So maybe you can consider combining the real equations with this corrected model, and that may be able to predict the shift of the critical temperature.
Yeah, very nice. Yeah.
Thank you.
Anyone else?
Can I ask for one more commentary, Professor?
Yes.
Go ahead.
In your hydrodynamic model, would it be better to take, for example, viscosity times the pore size as a more characteristic variable rather than viscosity? Because viscosity and thickness seems to be related.
Yeah. You mean here to,
instead of viscosity, can we consider a parameter like viscosity times thickness in pore size?
Yeah, it's a good, But we didn't look at this because, again, I mean, once we had this volume model, we were happy with this. But I mean, we were not against getting rid of the density of the viscosity. But no, I see what you I see what you mean, and that would be doable. Yeah.
Thank you.
Any more questions? All right. So I think it's time we wrap it up then. Once again, thank you so much, Dr. Coasne, for your presentation, and thanks everyone for the discussion.